Let's take a look at some conjectures. So remember, a conjecture is an unproven statement based on observations. And I'm going to make a lot of conjectures about even numbers, odd numbers, and prime numbers, so I guess I want to define those first. An even number can be expressed as 2 times n, where n is some integer. So if n was 4, it'd be 2 times 4, and it'd give you 8. It would give you an even number. An even number is something divisible by 2, and if you look at this, how I've created every even number, it's 2 times something. Thus, the number is always multiplied by 2, thus divisible by 2. And then an odd number is just an even number plus 1, or it could have been minus 1. So if you have an even number, if you go above or below 1, well then of course you're going to get an odd number. So if an even number is 2 times something, then an odd number is 2 times something plus 1. So that's even, that's odd. And then we'll use the word prime, a prime number. Remember, a prime number is a positive integer that has exactly 2 factors, 1 and itself, meaning it has no other factors. So like 12 is 1 times 12, but it's also 2 times 6 and 3 times 4. So 12 is not a prime number. Here are the prime numbers, at least the first so many of them. 2, 3, 5, 7, 11, 13, 17, 19, 23, right? And I've skipped over all the ones that have other factors, like 10. 10 has 2 times 5. 16 is 2 times 8. And so here are the primes, and there's an even and odd, and then let's make conjectures. Okay, so let's say I make a conjecture. 3 times an even number is odd. Well, algebraically, I'm saying 3 times some even number is odd, and that's really weird because that's got a factor of 2 right there, so it's actually got to be divisible by 2, and so it has to be even. But I don't even need you to prove it to me. All I need you to do, if you want to say something is false, all you have to do is give me one counterexample, because I'm making this conjecture, and that conjecture has to be true all the time, right? So I'm claiming that 3 times an even number is odd, and that's always true. Well, here's a counterexample. 3 times an even number of 4 is 12. There you go. So this is false. Again, to prove something false is really easy. All you have to do is provide one counterexample to show me that it's false. And then it's obviously not true for all things, and so then it's false. Okay, 5 less than all prime numbers is prime. Okay, so here's a counterexample. I'm going to claim that this is also false. Right, I'm going to say 17 minus 5, meaning 5 less than the prime number 17, that's 12. 12 is not prime, thus this is false, right? 5 less than all prime numbers is not prime. That's just silly, right? I'm sure it's possible to find one, right? I mean, 5 less than that prime number is 2, but this is saying 5 less than all prime numbers is prime. No, false. Counterexample. An even number plus an odd number is even. An even number plus an odd number, well, that even number plus that odd number is odd. And so this counterexample, again, proves this false. It's very easy to prove things false. All you need is one counterexample. To prove something is true, it'd be more difficult. If we really wanted to say it's some even number plus some number, some different odd number, we would have to do something like that. And I think on the next page, I'll really look at proving something like that. The sum of 4 consecutive positive integers is odd. All right, well, let's look at this example. How about 4 plus 5 plus 6 plus 7? So that's 4, 9, 15, 22. Well, I just gave you a counterexample that the sum of 4 consecutive integers is actually even. So this is also false. Again, proving something false is easy. Just give me a counterexample, just one. Again, because if this is going to be a true statement, it has to be true for all of those conditions. Okay, now let's go a little more in depth, and I'm going to do some even and odd proofs just because I think they're fun and it gives you an idea of what a proof might look like. I'm going to prove to you that even times odd is even. So this is my conjecture, and I'm actually going to prove this to be true. An even number is 2n, and I'm going to multiply by an odd number, so 2m plus 1. And I'm going to show you that it's also an even number. I'm going to distribute that n inside, so I'm going to leave that 2 right there, and so then the inside is 2mn plus n. Well, look at that then. This whole thing is just a number. I don't even care whether this number is even or odd. I'm not actually even sure. The point is it doesn't matter. If 2mn is a number, plus n is another number, but you're going to take that number times 2. But if you're multiplying it by 2, then it has to be even, meaning look at the original number. The original number has 2 as a factor, which is what I'm kind of showing you here. So this is really just 2 times some number w, where w is this whole thing. The only thing you have to show me now is that, look, it's got to be even. It's 2 times something, right? It is divisible by 2, so check. It's kind of like a fun even odd proof. How about even plus odd is odd? So even plus odd is going to be an odd number. And what you can do here is you can factor out a 2 from the first things. And then what do you know this number is? This is just some number, but this number times 2, this has to be an even. And then an even plus 1 has to be odd. Again, so these are kind of like very informal proofs that I'm happen to be proving these conjectures true. Okay, how about some more geometric conjectures? I'm going to say that a squared plus b squared equals c squared is true for all triangles. So any 3 sides of a triangle, that's true. So what if I take the triangle that's, what if all the sides are 4? Does 4 squared plus 4 squared equal 4 squared? Of course not, right? That is not true. I just gave you an example that a squared plus b squared equals c squared does not work for all triangles. So this statement is false. Hopefully we're at the point where we know that the Pythagorean theorem is only true for right triangles and right triangles only. And again, that is specifically where a and b are the legs of the right triangle and c is the hypotenuse for a triangle. Okay, and then the last one. How about if I made a conjecture that adjacent angles will always form linear pairs? Okay, so I could give you an example where these angles are adjacent, angle 1, and they're a linear pair. But if I give you one example that doesn't prove this true, I'd have to look at all the possible scenarios. However, to prove it false, I just got to give you one example where it's false. And now look at these angles. Angle 3 and angle 4 are adjacent, but they do not form a linear pair. So this, of course, is false. Just as a reminder, I gave you an example here that made that true, but that does not prove that it's true. That's just an example that works. You would need to prove it true for all things. However, to prove it false, you just have to give me one example that shows that this is actually false. I gave you an example where adjacent angles do not form a linear pair. Thus, the conjecture, adjacent angles will always form a linear pair, is false. Okay, hopefully this gets you started on conjectures, reintroduces you to like evens and odds and primes, and you can get started on our logic and reasoning worksheet.